All right, so we're going to start today just by kind of putting a cap on what little we need to cover out of chapter one. And for the most part, it's going to fall into basically two ideas, just kind of finishing the conversation from yesterday about what stuff is and how that kind of fits into what chemistry is. And then getting into kind of the basic fundamental idea of what science is, talking about the scientific method. So if you go back to where we were yesterday, we talked about idea that chemistry is this study of the processes and reactions and composition and properties of matter. And that matter is just some substance, anything that takes up space and has mass. Well, when we get into talking about chemicals, well, chemicals are kind of the same thing. Chemicals are composed of matter. They are substances that have the same composition, the same properties, regardless of where you find them. And what's important for us to understand and to know is that chemicals are all around us at all times. They're in every product that we have, every product that we use. And so the example your book gives is that of toothpaste. And you can look at toothpaste and see that inside of toothpaste, there are a series of substances that make up that toothpaste. Things like calcium carbonate, which is basically just an abrasive. It's something that is put into the toothpaste to be rough so that it helps to scrape off the stuff that's stuck to your teeth. Things like sorbitol, titanium dioxide, methyl silicate. And the processes of the purposes of all those there, they all serve some particular function associated with the toothpaste itself. And that's completely okay. So what I want us to think about is helping us to kind of differentiate what constitutes a chemical versus something else. So if it's chemical, then it has to have some sort of compositional feature. It has to be made up of matter. So I've got four things there on the board: sunlight, fruit, milk, cereal. Three of those things contain chemicals. One of them does not. Can we figure out which one is the one that does not? Sunlight. Yes, we can look at all of those other things and realize, okay, they're physical things. Fruit is a physical thing. It contains a variety of different substances in it. Milk is a physical thing. It contains a variety of different substances also. Breakfast cereal, same thing. The only one that doesn't contain chemicals is sunlight. And the reason it doesn't contain any chemicals is because it's not physical. Sunlight is energy. And energy has no mass, has no space. It's something completely different. And that is what makes it not a chemical. So we want to pivot from that kind of preliminary discussion of matter. We're going to come back to that here in a few minutes. We want to end our first chapter here by talking about the scientific method. And I want this to be kind of a personal process for you. I'm not just going to give you the ideas. I want you to kind of think about them and kind of construct them on your own. So when you hear scientific method, what are some things that pop into your mind? They don't have to be a full-on process. It can just be a couple of keywords, ideas, things maybe that you've heard before. But what I want you to do is kind of jot those ideas down somewhere, piece of paper, inside of your notebook, on your computer, wherever. And then after you write those down, take just a couple of minutes, share it with the person next to you. See if you guys can kind of come up with anything collectively that has some common ground to it. And then we'll talk about it together as a group. So let's take about 3-4 minutes, get your ideas on paper, and then start brainstorming with other people. All right, let's bring it back to front here. Heard someone say it feels kind of like a 7th grade science project, kind of, and in ways it does. We have to start simple. We have to kind of start from the ground up in order to get a really good understanding of what it is that we are trying to learn here. So just give me some ideas. What are some things that we talked about? What are some of the essential elements of science that we can kind of bring out here? So somebody give me an idea. Go ahead. Okay. Observations. Hypothesis. Those are good sciencey sounding words. Okay. Experiments. Yeah, go ahead. Okay. Data analysis. Okay. Okay, so we've kind of hit on all the high points here. Let's see what your book says. Your book calls the scientific method a set of principles that help to describe how a scientist thinks. And I would actually even modify that a little bit. Yes, this is a science course. This is kind of, we're trained to think about things as scientists. But the scientific method is something that you can apply to any kind of critical thinking process. It doesn't have to be a scientific process per se. You make an observation of anything. Doesn't have to be nature, doesn't have to be the natural world. It can be a political question. I observe this is happening, and here's my hypothesis for why it is happening. You can go through this series of steps for a lot of things that don't ever involve a laboratory. But when you go through this kind of methodology, this overall process, there are going to be some steps that you take along the way. One of them is making observations. One of them is trying to come up with some kind of an explanation for those observations. And that's where we come up with this idea of a hypothesis. A hypothesis has to explain why something occurs. It can't just be a statement of what. Statements of what fall into a different kind of category of scientific thought. That's getting more into the ideas of a law as opposed to a hypothesis or a theory. A law is something that we can state will happen every time, and we can just state what it is. Gravity causes objects to fall. I'm not explaining why, I'm merely stating what happened. That's a difference between these ideas of hypotheses, conclusions, theories, and laws. And the two sides don't talk to each other. Well, I won't say that. They don't interfere with each other. A theory doesn't ever become a law. A law was never a theory first. Because when you get through that hypothesis phase, the next step is an experimental phase. And in that experimental phase, you're going to test the hypothesis and see if your explanation for why that observation happened actually addresses the question, is it actually happening? And is your explanation valid, correct, makes sense? We mentioned the idea of data analysis, that part here. The last step would be a conclusion. I had this hypothesis. I ran this experiment to test the hypothesis. And the result of the experiment says the hypothesis was either correct. Sometimes we use the term valid in place of true, or our hypothesis was incorrect or false. The other thing that we have to recognize for the scientific method is that it is a process. It is ongoing. Just because something makes its way past conclusion and into that theory space doesn't mean that it is perfectly valid and correct forever. New things come about, new technologies exist, and suddenly the things that we thought were true aren't necessarily true anymore. For years, it was well thought that when something burns, it is burning up a substance within itself called phlogiston. And when the phlogiston is gone, the thing can no longer combust. The thing can no longer burn. Well, that was before they knew about oxygen. And when they found out about oxygen, suddenly the idea of phlogiston didn't make sense anymore. Because yes, you can look at a candle and say, oh, a candle is burning. And as it burns, it's getting smaller and smaller and smaller. And the hypothesis that something is going away kind of makes sense in that circumstance. But it isn't until you start to analyze, oh, hey, wait, that stuff that was coming off of the candle, that stuff has mass too. If I burn something, it actually gains weight. It doesn't lose weight because we're adding oxygen. And so the phlogiston theory goes away once Joseph Priestley starts to investigate and discover oxygen as being that gas that is present when things burn and allows things to burn. So science is an ongoing process. And notice again, there are two separate tracks here. The law track and the theory track are in completely different zones. They don't link together. One doesn't become the other. They're addressing different questions ultimately. A question of what versus a question of why or how. As I mentioned before, we can start to think about these things in a more kind of personal, everyday kind of circumstance. We don't have to just rely on the laboratory as a place to use scientific method and scientific thinking. So take, for example, some things like this. Let's say that you notice that you go to a friend's house and they have a cat, and when you're in the friend's house, you start to sneeze. Easily observable event. You can put yourself in that scenario pretty quickly. One possible explanation for you sneezing, maybe you're allergic. Especially when you consider that allergies can develop at any time over the course of your lifetime. You're not necessarily born with allergies. Maybe you're allergic to cats. Experiment to test that. You go to another friend's house who has cats. You act funny there too. Maybe you do, maybe you don't. But you could use the results of that separate event to tell you whether or not you might have reason to believe that you're allergic. You can take on more observations. You're at that first friend's house, you leave their house, suddenly you start feeling a lot better. Okay? Doesn't necessarily confirm that you're allergic. Could be that your friend just keeps a messy house and you're reacting to something else in that house. But a possible explanation is the cat also. So you'd have to do more experimentation to finally come to some kind of a conclusion about whether or not you were allergic. Another possible experiment, you go to another friend's house. You can start to begin to develop an idea. The more and more evidence you have, the more and more you can start to move for that idea from being a hypothesis to getting to something more concrete as a conclusion. Now, in the case of allergies, allergy testing is probably the best way to confirm if you're actually allergic to cats or not. But if you had a series of repeated incidents where you kept seeing the same thing over and over and over again, yeah, your natural inclination would be, well, maybe I need to think about, do I take an allergy pill before I go over to her house? Or is it okay to be in the room and just not touch the cats? Depending upon the severity of the allergy, it could be a lot of things. All right, let's see if we got the idea of our scientific method pieces here. We've got three things here. We want to identify them as either an observation, a hypothesis, an experiment, or a conclusion. So let's start with this first one, letter A. During a visit to the gym, your trainer records that you ran for 25 minutes on the treadmill. That's an observation, absolutely. Scientific studies show that exercising will lower blood pressure. Okay, we got some difference here. Okay. Back there, we said it was a hypothesis. Okay. Okay. Okay, that's the direction I would be going as well. The studies have already been done. So we've gone beyond this just being an educated guess, an explanation. This has now been at least in part validated by some kind of experimentation. So the studies themselves would be the experiment. But what they are saying, the link between exercise and blood pressure, that's a conclusion. Well, so conclusion and theory kind of are in the same boat, but they're different from a hypothesis. A hypothesis would be an idea, an explanation prior to testing, prior to experimentation. Since the experiments have already been done, we can't think of this as merely a hypothesis anymore. We have to think of it in some kind of way as this is a concluding statement, because we now have evidence to support it. Whereas with a hypothesis, we don't necessarily have the evidence. All right, letter C. Your doctor thinks that your weight loss is due to increased exercise. This one is a hypothesis. Keyword there, thinks. There is a preliminary causal relationship between these two. But we don't have very much evidence to show that it is directly one leading to the other. Could we get there? Sure. Your doctor puts you on a continued exercise program, and we see if you lose more weight or if you maintain your current weight loss. But equally likely, maybe you got sick before your doctor's appointment. Maybe you've only been doing the exercise regimen for a week and a half. Not a whole lot happens in a week and a half. Maybe in addition to doing the exercise, you're on a diet regimen. Okay, then it gets really confusing because now you've got two factors, not just the one. And how do you attribute weight loss to one factor versus the other? It'd be really difficult. So at that point, hypothesis makes the most sense. All right, let's look at some other ones here. A blender does not work when we plug it in. Observation, hypothesis, experiment, or conclusion. If it's a conclusion, it has to answer the question, why? This is just a what. This is an observation. All right. Letter B, the blender motor is broken. Okay. If letter A is my observation, letter B would be an appropriate hypothesis for that. What about letter C? Also a hypothesis. So what we're dealing with here is I've got a blender that's not working properly. I start to think about ideas for why it's not working properly. And so maybe there are multiple hypotheses there to think about. So, is it an issue with the plug itself? Is it an issue with the motor? Is it the outlet is malfunctioning? You can look at a number of different kind of things. And you go to letter D, I plug the blender in a different outlet, it still doesn't work. So there were two different answers stated, and they're both correct. This is obviously an experiment, but we're also looking at an observation from that experiment as well. The experiment itself is we're testing the blender in a different place. The fact that it still does not work is an observation of that experiment. We're collecting data, we're collecting evidence in that spot. observations are a form of evidence. The blender needs repair. Conclusion. All right. Any questions about the scientific method before we kind of move away from chapter 1 and get back to matter at the beginning of our chapter 3 here? Yes, sir. So what we have to think about is experimentation will always involve some level of observation. There's going to be some level of data collection that goes into it. Now, sometimes the data collection is very quantitative. We're going to be, collecting numbers on things. It takes 30 seconds to run 200 meters. It takes this amount of time for the car engine to start. We use the bread works when we use 1 tablespoon of yeast. It doesn't work when we use 2 tablespoons of yeast. Those kinds of things are quantitative observables, but they're also qualitative observables as well. I put this with this, a brown gas forms. I do this, this happens. And so all of that is data. All of that is observable stuff that we can use within an experiment to help test the hypothesis. So there's a lot of overlap between the parts and pieces of the scientific method. You don't want to think about it as step 1, I do this, then step 2, I do this, then step 3, I do this. These branch all over the place. Experiments yield observations which help to change my hypothesis. Experiments yield observations that validate the hypothesis. I start to make a conclusion. Conclusions themselves can help me to go back and revisit my hypothesis, especially if the answer is no, my hypothesis was incorrect. So the scientific method is not a linear kind of pathway. It forks, it branches, it cycles. So when we think about scientific thought, that's kind of the mindset that we have to take. It is divergent, but then it also comes back around to reestablishing a new idea, a new hypothesis, a new theory eventually.